When we first learn chemistry, we start with these perfect, beautiful models for how everything works, atoms bonding together in these really neat and predictable ways. But what happens when the real world, doesn't quite play by those perfect rules? Well, that's what we're diving into today.
So, we all learn about methane, right? CH4. It's kind of the poster child for sp3 hybridization. You've got a central carbon, 4 hydrogens, and they all arrange themselves in this perfect tetrahedron. Every single bond angle is exactly 109.5 degrees. It's clean, it's symmetrical, it's our gold standard.
But then you look at a molecule that's, let's be honest, even simpler. Good old H2O, water. The oxygen atom in water is also considered sp3 hybridized. So, shouldn't its bond angle also be 109.5 degrees? But it's not. It's 104.5 degrees. That's almost 5 degrees smaller. What is going on here? This is the puzzle we're going to solve.
So let's just put this side by side. On one hand, you have our expectation from the simple model, this perfect, symmetrical 109.5-degree angle. On the other hand, you have the reality of water, this bent, V-shaped molecule with a much smaller angle. Now, this isn't just a rounding error. This is a major clue that something much deeper is at play.
All right, so this is where things start to get a little weird and a lot more interesting. Let's really dig into why these perfect geometric rules start to fall apart.
Now, the first explanation pretty much everyone learns is called VSEPR theory. And the idea is pretty straightforward. Electron pairs hate each other and want to get as far apart as possible. VSPR says that lone pairs, the ones not in a bond, are kind of fatter and take up more room. So in water, the 2 lone pairs on the oxygen push the 2 hydrogen bonds closer together, squishing that angle. And honestly, that's a pretty good start.
It's a solid theory for sure, but is it the whole story? I mean, if it's all just about fat lone pairs pushing things around, should that explain every single case we see? Or is there something more fundamental happening? Let's look at the evidence.
Okay, now check this out. This is where it gets really telling. All of these molecules have a central oxygen with 2 lone pairs, so VSEPR theory would kind of predict a similar squishing effect for all of them. But look at the actual angles. When we attach these big electropositive methyl groups, the angle is actually wider than 109.5 degrees. And as we swap those out for more electronegative atoms, first hydrogen, then fluorine, look at that. The bond angle just keeps shrinking step by step.
You see that? This isn't random. There's a clear, predictable trend here. The more electronegative the things attached to the oxygen are, the smaller the bond angle gets. This tells us that it can't just be about lone pairs or fat. We need something deeper, a more powerful rule to really explain what's going on.
And this is where the hero of our story comes in, a chemist named Henry A. Bent. Back in 1961, he came up with this really elegant and powerful idea that just clicks everything into place. It's called Bent's rule.
So here it is in all its glory. Now, I know, that sounds a little dense. Atomic S character concentrates. What on earth does that even mean? And why is this S character the key to this whole mystery? Let's break it down.
Okay, think of it like this. An atom has different kinds of orbitals, mostly s and p orbitals. S orbitals are spherical, and the important thing is their electrons can get right up close to the nucleus. P orbitals are shaped more like dumbbells, and their electrons are generally a bit farther away. So because s orbitals are closer to the positive nucleus, the electrons in them are held way more tightly. They're at a lower, more stable energy. They're prime real estate.
So here's how the atom plays its cards, and it's all about saving energy. An electronegative atom, like fluorine, comes along and it's a real electron hog. It starts pulling electron density away from our central oxygen. So the oxygen atom does something incredibly clever. It says, fine, you want to pull my electrons away? I'm not going to put my best, most stable s orbital electrons into that bond. I'll use an orbital with more p character, since those electrons are higher energy and further away anyway. This move lets the oxygen save its precious low-energy s character for its own business, like for its lone pairs.
And this right here is the golden rule, the big geometric consequence. Orbitals with more s character are kind of fatter, and they naturally create wider angles. Orbitals with more p character are skinnier and make smaller angles. It's a direct relationship. The more s character you put into your bonds, the wider the angle between them gets. It perfectly explains why the angle shrinks as we go from dimethyl ether all the way to oxygen difluoride.
Let's put this to the test with an even trickier molecule. In this trigonal bipyramidal shape, you've got 2 different kinds of positions,
the axial ones up and down, and the equatorial ones around the middle. It turns out the axial positions have less S character. So what does Bend's rule predict? It predicts that the most electronegative atoms, the fluorines, will go to the positions with the least S character. And guess what? That is exactly what happens in reality. It just works.
And the amazing thing is, Bend's rule isn't just a one-trick pony for bond angles. Because more S character holds electrons closer and tighter, it also explains why those bonds are shorter and stronger. It helps us understand data we get from lab instruments, and it even helps explain how electric charge gets passed along through a molecule. It is a really fundamental, powerful idea.
So where does a rule like this fit into the grand scheme of chemistry? Well, for that, we need to open up the chemist's toolkit.
The thing is, in science, there's almost never one single theory that explains absolutely everything. It's more like having a toolkit. We have lots of different models, and we learn to use the right tool for the right job. VSEPR gives you a quick and dirty guess about the shape. Bend's rule comes in and refines that guess with incredible precision. And other theories, well, they answer totally different questions.
For instance, Bend's rule is part of what we call valence bond theory, which thinks of electrons as being stuck in a bond between two atoms. But there's a whole other way to look at it, called molecular orbital theory, which sees electrons as being spread out over the entire molecule. That theory is way better at explaining weird things, like why liquid oxygen is magnetic. So you see, different tools, different jobs.
Okay, we have gone from perfect tetrahedrons to weird bond angles to the subtle ways atoms manage their orbitals. So after all that, what is the most important thing to remember?
I think it's this. Simple rules are a fantastic place to start. But the real understanding, the real beauty of chemistry, comes when you start to ask why the rules break. It's in understanding the deeper principles that explain the exceptions, that's where the magic really is.
Bend's rule is so cool because it shows us that atoms aren't just these boring, static things. They're incredibly dynamic. They're constantly adjusting, fine-tuning their bonds and their orbitals, all in a constant search for the most stable, lowest energy setup they can possibly find. It's an absolutely elegant system.
And that kind of leaves us with one last thought, right? We started with a simple rule that we all learned, and we found this much richer, more fascinating story hiding just underneath. It really makes you wonder, what other simple rules out there have a much deeper story just waiting to be told? Thanks for joining me on this one.